estamos yendo al vivo, sí. Ahí estamos.
Bueno, hola a todos, bienvenidos, bienvenidas. Hoy estamos en un nuevo coloquio del Departamento de Física y hoy tenemos un invitado que no habla español, así que voy a pasar a presentarlo y a saludarlos a todos en inglés. Espero que me salga lo mejor posible. Vamos a presentar, hello, Félix Bussières, who is here. He's originally from Canada, where we met. He did his master physics at the University of Montreal, then a PhD at the École Polytechnique de Montréal, and then he was a postdoctoral researcher for several years at the Group of Applied Physics in the University of Geneva. And since 2016, he works at Quantique, which is a company. He will talk about that. And from the last 2 years or 3, he has been the vice president of the research and technology part of the company. So we are very pleased to have you here, Felix. Thank you for agreeing to do this seminar with us. And well, we are free to be listening to you. Thank you for being here again. You can share now your screen.
All right, good. I will do that. Okay.
Yes, we see everything. Screen? Yes, okay. Everything is perfect.
Great. Well, let me also thank you very much for giving me the chance to talk about some of the things we do at IDQ. It's great. We're very far from each other physically, but we can be all together to talk about physics, talk about applications of the quantum technologies, things that IDQ is focusing on. And also talk about, well, really like go on a couple of topics that I hope will be of interest to you. The world of quantum technologies, you may have heard about it, especially recently, is really expanding quite a lot. There's a lot of investment in it, like for instance in quantum computing. I'm sure you've heard of this. There's really a lot of interesting things happening, and I've been in this field for many years now, and it's very an exciting time, and IDQ is part of it, and I want to tell you about a few things we do here in that context. So I'm a physicist, as Laura said. Now I work in a company that is doing R&D, but is doing products. We're not doing just R&D as something that may be out there in a couple of years. We're really working on things that are out there or that are going to be out there very soon. And it's very interesting. If you have any questions related to that, I'll be happy to let you know. When I was a physics student, didn't get a lot of chance to ask about these things. So if I can help anyone by understanding that better, I'll be happy to do that. So, all right, let me just reset the timer here so I can follow properly with respect to the time. So I want to talk about two main topics here. One is quantum random number generator and its security. And the other one is superconducting nanowire single-photon detectors and some applications of them. These are technologies being developed by IDQ and are evolving and so on. And I will tell you about the physics, but also the applications themselves. So let me start with the QRNG chip. Okay, so random numbers. Random numbers are fundamental in security. At IDQ, we have two divisions, let's say units. One is quantum safe security. Quantum safe security is when you try to use quantum mechanics in order to do things that will provide security in communication, for instance. Okay? And IDQ is developing different levels of technology, and there's different ways to use these, or different steps in which you can use these technologies. So IDQ is often talking about the path to quantum safety. And the first step towards this is actually the generation of random numbers using a QRNG here. And this is what I'm going to talk about. The second step is what we call crypto agility. So encryption is evolving quite rapidly. Standards are changing. There are institutions like NIST in the US that are preparing for a future where a quantum computer is going to be there. And this is going to impact currently used method for encryption. So you have this aspect there that will require a quantum random number generators, other kinds of encryption algorithms. And the last step, which is really the ultimate step that covers all the box in terms of security, is quantum key distribution. Now, I'm going to start, essentially, if you want to be quantum safe, you have to go through these different steps, and you want to choose the technology that fits your application case here. And here, the first step is this QRNG. So this technology here actually goes into devices that are being used out there. So let me dig a bit deeper with respect to that technology, this QRNG. Okay, so random numbers. Now, I'm not going to explain that in details, but essentially, if you want to communicate in a secure way, Alice needs to talk to Bob. So one way to do that is to have Alice to generate a sequence of random numbers. And this needs to be given to Bob in a secure way, or the most secure way you can do it. And then once these two have that, then they can use an encryption algorithm to do that. Now, this can also be used as an input for quantum key distribution, but I won't go into that. But these numbers, they have to be secure. And a way to do that is to use quantum physics to actually generate these random numbers. So why do QRNGs actually help? And that's the important message here, is that they provide a clear and robust entropy generation mechanism. Entropy in terms of random bits that are going to be produced by the device, and you can have a physical security proof. So what we want to do at IDQ is to make them widespread quite a lot, and you need a couple of items in order to do that. One of them is that their production cost has to be low enough for mass market, so something that is CMOS compatible ICs for large-scale production, it helps quite a lot. A small footprint, a low power consumption, and then, of course, compliance with some security standards. I won't go into detail. And that's what we do here with this chip here. So I want to talk about the physics of that because it's actually quite interesting. The original idea behind this QRNG chip, that is a device that we make at IDQ, comes from this paper here. And the paper talks about doing a quantum random number generator in a mobile phone. Why a mobile phone? Well, the idea is that you have ingredients in a cell phone that allow to do this QRNG. And that's what I want to talk about here. So the model of a camera, okay, is that you have a bunch of little pixels, and every pixel, and you have millions of them in a camera. Each pixel can be modeled as something like this. You have light that comes in, there's some loss. It's like a beam splitter in optics. You have a detector, so something that accumulates a certain number of electrons, and then these go into an amplifier, which transforms the number of electrons into a voltage, and that is read by an analog to digital converter circuit. So a certain number of electrons is going to give an output that we call an ADC code. Okay? Now, the cameras you find in a cell phone are called a CMOS image sensor, where each pixel is that, what I just explained. And they're very low noise, and they have a very high detection efficiency. QE is for quantum efficiency. So the property that a photon generates an electron that is captured is quite high. So if you have this, and you have it in your camera, it's CMOS compatible and so on, can you benefit from the fact that you have a lot of these and produce a lot of random bits? Okay, so you take that, you go into a randomness extractor, and you produce a random number. This was the idea of that paper there. And what they were doing then is that they showed that when you eliminate that with light, okay, to be technical here a bit, it's a multimode thermal source that leads to a Poisson number distribution. So each pixel, whenever you expose it, it's going to accumulate a certain number of, it's going to absorb a certain number of photons that is going to create a certain number of electrons, and it's random. What you get at the output is random, and the source of the randomness is the quantum nature of light. So this is where the quantumness in the random number generation actually comes from. And if you look at one pixel, at the time they used a Nokia phone, if you look at one pixel, you're going to see every time if you plot the distribution of the number of electrons that came out of one pixel, you're going to see a distribution. And this distribution, as I said, is directly correlated to the quantum nature of the light that you have there, the statistical nature of the number of photons that you had at the input. And you have this distribution. And distribution is not due to the noise, it's really due to the photons. And actually, it turns out that the distribution has a Poisson form. It's multimode, thermal, it gives actually a Poisson. The noise of one pixel is really, really small. The noise when you have nothing, you have this distribution here. So this is stray electrons not coming from photons. So the width of that is much bigger, so it's dominated by the light there. So the way to generate randomness out of that is to, you don't know where you're going to land when you expose it once. So you take that and you put that into an ADC, which generates a sequence of bits, where you have the least significant bit here and then the most significant bit here. It's a 10-bit ADC, okay? So if you look at what happens here, well, this bit is actually influenced by the classical noise, so you don't want to look at this one. These bits here, actually, they never fluctuate because they represent the highest number in the number you're going to draw at random. But these bits here in the middle are the ones that actually fluctuate due to that distribution here. And actually, you can show that the amount of entropy, number of really random bits you can extract from that is about 5.7 out of that. So in order to extract the randomness out of that, you have to do a software process where you do randomness extraction. And at the time, this was done outside of the phone because it's actually demanding. You needed to have a dedicated circuit for that. Now, if you want to take that and put it into a phone without having to do that, there's an easy trick. You can keep only these two bits here, bits number 2 and 3. Okay. So if you don't use all of that, you're going to have something random. And this is what I want to talk about here. Okay, so let me just go over it again. You have this light source, which goes into the CMOS image sensor. You have the filtering, the ADC, and then the filtering, meaning you keep only these two bits here. And then you have random bits coming out, which what we call the quantum entropy. And again, the randomness comes from the Poisson distribution that you have in terms of the number of photons that you have at the input. Now, if you keep only these two bits here, it means you're going to have, every time you expose a pixel, each pixel is going to give 2 bits, 0, 0, 0, 1, 1, 0, or 1, 1. And if you want to know which one you're likely to get, well, you can look at this whole range here. As I said, you draw a number at random, and it turns out that if you keep only these 2 bits here, you're going to divide this range here into smaller sections, and each color shown here represents one of the four possible sequences, 0, 0, 0, 1, 1, 0, 1, 1. And you see that if you put this whole thing here and expose this and slice it with that, all of them are pretty much as likely as the other ones to come out. And you see that you're as likely to outcome any of the 4 possible 2-bit sequences out of that. Okay, now let's go into the physics a little bit more. Okay, so what happens is that the detector, each pixel goes, well, the physics is like this. You have a certain number of photons, which goes into the device that has a certain efficiency, and that creates a certain number of photon-generated number of electrons. This is going to be mixed with another source of noise, which is classical noise, so to speak. These are stray electrons. They're not coming from the photons. They go together, and then you have this conversion here and to a voltage. So here you have a random voltage, and then you go into the ADC. Okay, so these are dark electron noise. In a way, we don't consider them to be coming from the quantum part. And then you also have Gaussian electronic voltage noise, which we also don't consider to be contributing to the randomness of the output. And you look at this whole thing, you try to model that, and you try to see what happens. Okay, so there is a conversion with the gain, and we name it K. Okay, and K is actually, you can simplify the whole thing and say that the K value here is essentially the fraction of one ADC code step provided by one electron. So the ADC it's a 10-bit sequence, so it's a number between 0 and 1023, so 1024, which is 2 to the 10. Now, whenever you have one more electron, you are going to increase the number here by the value k. And it turns out that you don't always go by one number here. Sometimes, if you add one more electron here, you're going to go over one number at the output, and then another one, you go over one other number, but then the next one actually falls short. So it's possible to have two electrons that don't make the number here increment by a number of 1. You always have this mismatch here. So if you look at the distribution of the number you get there for a given intensity at the input, you're going to have a distribution, as I said, which comes from the photon number distribution, but you can have this spiky structure here, which comes from this effect here. I'm going to call this the pileup effect. So interestingly, you really see, in this, you see the effect of the photons one by one in a device that is on your cell phone. So it's quite interesting that quantum physics is really there in the pictures you take with your cell phone. You have these quantum effects in there. Now, if you take that effect into account and you look at the property to draw one of the 4 sequences, they're pretty much the same. There's some slight difference due to that, and that may depend on where you are. But you have an entropy. Okay, the entropy here is a measure of how random it is, this 2-bit sequence. If it's perfectly random, this min entropy is equal to 2. And what you see from a simulation here at this point, it's almost equal to 2. So it's close to being optimal. Just directly from eliminating a pixel in a camera that you have on your cell phone. Now, this is great, but it also needs to be robust, because if you put that into the hands of somebody, that you want to make sure that it's working properly. So you need robustness to light intensity fluctuation, and you also want to do a bit of drift compensation. So this is, in a way, you can see this as the intensity of the light, and of course it's going to fluctuate. It's never perfect at one value. What you see here, again, is a simulation, is that if you move the intensity of the light, the entropy stays flat over a broad range. So if you control the entropy well enough and you never go out of this range, then it's actually going to be quite robust. So that's something that's quite important. Okay, so those were simulations. Let's go to measurements here. Here I'm showing distributions for 4 different intensities of light. So higher intensity, lower intensity. You see these distributions, they move like this, it's normal. Now, there's a couple of things that you need to take into account. Now, the whole array is not uniformly exposed. It's also important to realize that, and that's why this robustness is important. But if you look at these numbers, you notice that actually you do see the pileup effect that I was mentioning, okay, which was expected. And then the width of the distribution changes with the intensity, and that's consistent with the Poisson distribution. In a Poisson distribution, the characteristic is that the width of the distribution, the variance, is proportional to the mean of the input. So it should become wider as you increase the intensity, and that's what you see there. Now, more specifically, in that device, you should have a relationship that is linear between the variance and the mean, and that's what you get there, which shows that it's behaving like it should. That is, you're seeing a Poisson distribution that actually comes from the photon at the input. Okay, so now you look at this whole thing, and I remind you that you have this model here with this extra noise that actually comes in. So how do you see this extra noise? One way to see it is to switch off the light, and you have everything that's close to 0, because when you have no light, you should have 0. But in practice, you don't have 0. You have a little structure. This is the electrons. You see, like, the number here is 10, and when you eliminate it, you're more like at 500. So it's very close to 0, but you still have something. These are these dark electrons combined with the fluctuations there. Now, if you look at this, there's a structure. You have this width here, which is due to that, the Gaussian part, and you have the structure, which is the pileup effect of the dark electrons. So you also see this pileup in that structure there. So you look at this, and you actually see, you can get values for these numbers here, and you see how much noise comes in. Now, if you think about the security of a device, that's not something you control, and you may even want to assume that this is something that can be known to somebody who's trying to hack your device. So if you want to claim a quantum-only random number generator, you have to say that this information, this contribution to that can be known by somebody who's trying to guess what the random numbers are. So you can do that. Okay, so this is what we call side channel information. It goes into the device. So you have this quantum entropy input, you add some noise that can be known to Eve, the eavesdropper or the attacker, and you want to know what happens. Now, you see, this is very small compared to that, so it's not going to be influencing or biasing the output quite a lot. And you can run this into some calculations that take into account the amount of information that may be available to the eavesdropper, and you try to calculate what's the guessing probability of the eavesdropper given that, and then you recalculate the entropy given this information that Eve has, and you get this value here. Okay. Now it turns out that this is actually completely negligible. It really doesn't make a difference, which is great. And you have something that's close to optimal. So in the worst case, it's going to be around 1.95. And you have this region over which the intensity of the LED illuminating the CMOS image sensor is going to be controlled. So you're going to stick in that region. We did more tests that I'm not going to show here. We looked at the correlation between pixels. We didn't find anything. And our correlation from frame to frame, nothing there as well. Now, something that's quite interesting is that there's a failure detection mechanism in the device, which is such that, imagine the intensity actually goes on the side here, then the entropy is going to drop. So it's no longer outputting random numbers here. So you want to know if this happens. Now, the nice thing is that the device detects if the light is too low. And if the light is too low, you're still within a range where the entropy is good. So you're going to make sure that if the device fails, it's going to be still outputting random numbers until it actually fails. So that's quite important because you don't want this to go haywire and not have the security that it should be provided. You know, this is selling trust, something you can put in the device and forget and make sure that you the end user doesn't have to think about it. So it's quite important to have this kind of behavior there. So everything is put into a small processor. Okay, I'm going to skip the details, but the architecture is compliant with security standards. It has these live health checks, making sure that it's operating properly. It works in an autonomous way with auto calibration, and it can be used as a quantum entropy source directly, or you can put that into another section that's necessary to generate random numbers for a security application. It can be done all in there. And the interesting thing is that, you know, this is quantum physics in a way, right? That, but the whole thing is in a very small package. So there's a device that's made to be put into handheld devices, such as a mobile phone, which is 2.5 by 2.5 millimeter in size, okay? And it's going to output a number of random bits per second that is completely sufficient for pretty much all the applications that you can have on a cell phone, and it consumes a very small amount of power. So I think it's very interesting to see that such a device can be made, and the realization that you have this quantum nature in the device itself, it can lead to something that you know, is quantum enabled, and you can benefit from the security that it will provide. So at IDQ, we like to say that the quantum decade has begun. Now, actually, there are devices, mobile phones that are being made by Samsung, a model called the Galaxy Quantum, and there's even a version number 2 out there right now, which do have this QRNG chip. So it is, so this is just the beginning for us. I think we clearly want to get into a mass market with this in not only mobile phones, but a lot of other applications. And there's a lot more happening that I'm not going to talk about, but you see that this has reached a level where a quantum device can be in a mass market, which I think is a nice realization. And we think it's the first mass market application of a quantum technology, at least of that sort. So we're quite happy that we can have we can provide this kind of level of trust with those technologies that are out there. And let me remind you of the main point, which is that what I've shown is that we can know what's going on into the device. So you have a clear and provable security proof, physical security proof, and that's what this is what this device is actually providing. So if you could, I didn't talk about the other types of random number generators that are out there, but these are much more complicated devices, and they're often based on we think they're based on a chaotic behavior. And if it is chaotic, it's actually pretty good, but it can go sideways, and it can be made in such a way that it can actually stop working without you even noticing it. So it is important to provide this clarity in the random number generator that you have for security applications, and this is what this device is providing. So we have a paper published in Physical Review Applied. If you're interested in having the details, please have a look at this. Okay, so let me, if I don't think there's any question, if there's a burning question, I'll be happy to answer it. Otherwise, I'll move on to the other section of the talk, where I'm going to talk about superconductivity and single-photon detectors. So this work is set in the context of the other unit of IDQ, which is what we call the quantum sensing unit. So what we want to do in that section is to empower researchers and industries in advancing the frontiers of single-photon science and application. I come from an academic background, from a research background. I went into that because I wanted to, not only I was curious, but I wanted to have an impact in the world using the technologies. And this is what we want to do with that aspect there. And we want to be basically working with people that are at the first stage of these innovations and be able to enable them to actually have fluid and good research go forward with that. So we have different devices. On one end, we have low light level sensing devices, single photon detectors. On the other end, we have timing control, so something that actually records the detections of the detectors as a function of time and can do correlations, coincidences, and so on. This is used in pretty much all the quantum optics labs that have single photon detectors in the world. And you can take these together and do solutions. Quantum physics, of course, is a big area of ours, of these devices, but there are applications in free space communication, even deep space optical communication, a downlink with the laser from Mars to the Earth. Applications in imaging, life sciences, material sciences, a lot there. OTDR, LiDAR, so basically light imaging, also in security, surveillance, oil and gas industry. So there's a lot of applications. Now I want to talk about another fascinating technology, at least to me, where we use superconductivity to do single photon detection. So so these devices are called superconducting nanowire or nanostrip single photon detector. The acronym is SNSPD. Maybe you've heard of them. Essentially, what we do is that we create a device where there's a strip of a superconducting material. The width is around 100 nanometers, and the thickness is about 5 to 10 nanometers, something like that. It's cooled down to below its critical temperature, and then biased with a current that's below the critical current. And when a photon comes in, the energy of a photon is about 1 electron volt. It's going to break a lot of Cooper pairs. The energy of 1 Cooper pair is about 1 electron volt. So you're going to break about 1,000 Cooper pairs with 1 photon. That's going to create a region of weakened superconductivity. There's going to be an interaction between the current and that, which is going to transform that into a resistive region. And it's going to transition from no resistivity to something that has about 1 kilo ohm resistance in about 100 picosecond or even less. It's quite fantastic that you have a device that can switch, given 1 photon, from 0 to 1 kilo ohm so rapidly. It's very, very unique. There's no electronics that does that. There's no other electronic that does that. So this device, shape it in the form of a meander like this. You have the nanostrip that comes in here and then meanders around like this and then comes out. And then you bias it. So you take a bias current which goes into the device, okay, which can be modeled as an inductor and then a switch, either superconducting or resistive. And whenever there's a deflection, it's going to switch from that branch to that branch. And then the current is going to leave because the resistance is quite high. It's going to go into an amplifier. And then now this can cool down, become superconducting again, and the current can actually come back in. The time to unbias the detector is very, very short because the time dynamics is governed by the ratio between this kinetic inductance, which is a superconducting material property, divided by the resistance of that. So this is quite high. So the time constant L over R is very short. So that's going to give rise to a rising edge here at the output of this amplifier, which is very, very sharp. Then it goes down and it's rebiased again. But then the resistance dominating the time constant is not this one, it's this one, which is much smaller, typically 50 ohm. So then the rebiasing is much slower. So you have this very sharp rising edge and then this more slowly decaying falling edge. So it gives a device that it's operating in asynchronous mode. You don't need to know when the photon comes in to actually detect the photon. It's called also free running mode. And it just worked by itself. So IEQ were making these detectors. This started when I was actually at university, and then there was a technology transfer. So I moved with the technology to IEQ, and we've been developing it intensively since then. So detectors are made in Switzerland. The whole system is made in Switzerland. So actually, the system looks like this. It's a cryostat. This is about 65 centimeters high. This cools down to 0.8 Kelvin. So if you don't know about cryogenics, it's actually quite low, but it's not very complicated. It's actually relatively, the technology is out there to cool down to 0.8 Kelvin without any liquid helium. All this is closed cycle. You just started, 12 hours later, you're at 0.8 Kelvin. And there's, so with that system here, you're going to get SNSPDs, which are stunningly great in terms of performance. They're the best actually overall. So they're free running. The efficiencies can be really high, close to 100%. The noise is really, really small. I'll tell you more about this. The time resolution, that is the ability to locate where's the photon at a given time, is also excellent. And the recovery time is super short as well. So you can detect in the tens of megahertz range. There's also an upside with that. It's very broadband. So the efficiency can be broadband over hundreds of nanometers. And the reason is pretty simple. You know, if 1,000 Cooper pairs break superconductivity, well, 500 Cooper pairs broken will also break superconductivity. So if you have half the energy of your photon, you still break a lot of Cooper pairs. So it's going to be quite broad. And in a system like this, you can have up to 16 detectors. So it's really an enabling technology, and the quantum labs out there are good about it, actually. So there's a lot around the world. It really allows the research group to go beyond in terms of what they can do with their technology. So one slide about the broadband nature of the efficiency. If you look at what we can get, so here we have examples. This is a detector that was optimized for 1550 nanometers. A lot of telecom stuff is happening there, quantum communication and optical fibers, for instance, but also free space with satellite and so on. Well, you can have an efficiency that's quite good, and it's pretty much the same at 1310, and then it drops off. But then you can have another detector that can cover this range very, very well, and then another one that can cover this range very, very well. And they do detect. They do detect on that side, and they do detect on that side as well. So you can go beyond 1550, more towards mid-infrared applications. So that's actually quite nice of these devices. One interesting fact about that is that the noise in these detectors, so let's say you put a metal cap on the input, you're still going to get clicks. And you have more clicks here than you have there. And we call them dark counts. But they're not actually dark because they come from photons. They don't come from the device itself. They come from black body photons that find their way into the optical fiber. So depending on the type of fiber you have in the system, you may have a lot or less photons, and turns out that here you can eliminate the photons very, very well. Actually, at this wavelength, there's also less black body photons than around here. At room temperature, the maximum, I think, is around 3 microns. So you're in the tail of the black body photons, which goes down here. And that's what we see in practice. Okay, so here's an example of, admittedly, a very, very good detector at 1550 nanometers, where we have the detection efficiency as a function of the bias voltage. This activates the process to detect the photon in a way. It's also proportional to the current in the device. And the efficiency goes up, and you have a plateau here. So here the efficiency is stable. It doesn't help to increase the voltage anymore to increase the efficiency, and you're close to 100%. 95%. We also made some detectors that were beyond that, around 98% efficiency. Those are more difficult to find, but this is the technology. This is the technology that can actually bring that. You see the dark count rate is around 50 counts per second for that device, so less than 100. So if you have used, maybe some of you have used SPAD, so semiconductor-based single-photon detectors. I'm sure you'll see this and you're going to agree that this is really fantastic with what you, with respect to what you can have with the other ones. The other ones are still good. They're much cheaper, but in terms of providing super high performance, these are very, very good. Here's another example at 780 nanometers. You have a longer plateau. That's the physics that actually gives that. And with this wavelength, as I was telling you, we have less than 1 count per second at the maximum SDE. So here we're like at a fraction, like 1/10 of a count per second of dark counts. And so it's just phenomenal in terms of the signal to noise ratio you can get with these devices. Okay, so let me enter quickly into where these detectors can actually go. And this is the nice thing about SNSPDs is that you can cycle quite rapidly when you develop them, because it's not like you don't need a semiconductor foundry and spend thousands and thousands, tens of thousands of dollar or Swiss francs or whatever into trying to improve them. You can improve fast the devices and play with the design, and there's a lot of things that you can do with those. One of these things is photon number resolving detectors. So what I've showed so far are detectors that give you the same thing if you have 1 or 2 or 3 photons. It's the same output pulse. But you can make them in such a way that you can have photon number resolvability. So why do we need that? Well, actually, there's a big trend, you might have heard, in making quantum simulators and quantum computers using photons. And some argue that it's the only way that this is going to be scalable to 1 million qubits. Okay, we'll see what the future brings. But clearly, the photons have this advantage of seeing a route towards scalability towards a really large number of qubits that you would need for a full-fledged quantum computer. And there are some examples out there, just showing some of them, where a PNR detector is actually necessary to realize quantum algorithms. This is a paper that's very recent, which shows this in a very clear way. This is a company in Canada called Xanadu. They're using PNR detectors. So here's another example with continuous variable cluster states. I won't go into the details. And here, higher order Fock states with PNR. So definitely these photon number resolving detectors are necessary are a great tool to actually take the field forward. You might have heard about this experiment that was done in China and published in 2020, talking about the quantum computational advantage using photons. So this experiment had a lot of nodes, a lot of detectors, and very impressive optical table, definitely, and 100 SNSPDs in this. And then they have achieved to do something called Gaussian boson sampling in a way that they claim is untractable with a classical computer. Okay, so this is the second example of a quantum computational advantage. The first one was with superconducting qubits, an experiment done by Google. Now, in such an experiment, if you can actually put PNR detectors, you're going to make the demonstration even more strikier, even more stronger. So PNRs actually are going to help in something like this. Now, the best PNRs that you can get out there right now in terms of capability of detecting a lot of photons are transition edge sensors, another type of superconducting detector, not like SNSPDs. Now, in a nutshell, these devices are cooled to something like 50 to 100 millikelvin, so much colder in temperature than the SNSPDs. And then you position them right on the transition from superconducting to normal region. And let's say you're there. Whenever there's one photon, it's a bolometer. So whenever there's one photon, it's going to hop in, up and up and up and up and like this up to a certain point. And then you're going to get a signal at the output that's going to depend on the number of photons. This is a recent paper where you see that, these different traces and the shape of that, the area and so on. You can analyze it and determine how many photons were detected. And here, the nice thing is that the efficiency doesn't depend on the number of photons that you have absorbed. So if you have an efficiency of 99%, the probability of having 16 photons is 99% to the power of 16, which is actually still really, really high. And in that paper, they have shown a very high efficiency and the ability to discriminate a lot of photons. So they're really, really good for PNR. And they're close to noise free. Problem is that the temporal resolution is really bad. The recovery time is also really slow. You need a squid to read it out, and you need dedicated FPGAs, so it's kind of complicated. And there's no commercial availability of these, and they're slow. They're bigger, more expensive, probably needed. So one might argue that it's more difficult to consider these as the right route to have a quantum internet infrastructure or maybe a quantum computing infrastructure using that. So comes in SNSPDs, that's what I'm going to tell you about. That's something that we've been working on. And we use a different approach. So first approach we use is that we take the area where the photon can actually come in, we divide it into a couple of sections, and we connect everything in parallel. And you have to do this in the right way, otherwise it actually doesn't work. But if you do it like this, then you're going to have this device being able to detect a couple of photons. So that's what we see in this trace here, where you have different amplitudes. If you had one section clicking, you have this pulse. 4 sections, you have almost pretty much 4 times the amplitude. So you can actually know how many that you have there. And you can get towards very high efficiencies. We're working towards getting the whole thing towards 95% efficiency like we can do with a normal detector. And this is current development, but already people are starting to use that in order to enhance their quantum simulation, quantum computing type of applications, among other things. So this is an example that with 4 pixels, and this is an example with 8 pixels, where you clearly see if you take a slice of that, you have these different peaks, and you can know how many you have there. So it's a slightly different than a TES in the sense that in order to detect 2 photons here, they have to split. So there's a loss associated to the fact that they have to split, because if they both arrive in the same section, you're not going to have twice the amplitude, you're going to have once the amplitude. So in order to get close to what a TES can do, you need to have a lot of pixels. So there's an order in which you can go, but ultimately, you don't want to have 1,000 coaxial lines to read every pixel in the crosstat, so you need to have something scalable, and that's going to be done by using proximity cryogenic electronics. And this is something that we're working right now. It's also something that's useful for quantum computers for superconducting qubits. So really looking forward to have this come out, and hopefully, in some time we'll be able to tell you more about that. Okay, I see time is actually running fast. I'm going to have to skip some slides, and I apologize for this. I want to move on to the space launcher part and finish with this here. So quantum technology, am I right? Yeah, I'm right. So quantum technologies are not only for quantum optics lab, they're also for very serious applications like this Ariane 6 launcher. So the European Space Agency has this space launcher program, the Ariane program, and right now they're still running Ariane 5, but they're working on Ariane 6, and the maiden flight should be in 2022. It's been postponed because of COVID, but it should be in 2022. Now, they have made one innovation in this, which is optopyrotechnics. So let me explain what this is. Okay? When you have a space launcher, you basically first need to start the engine, and you have separation of the different stages. and then in the end you drop the payload. So all of this requires pyrotechnics to separate the stages, also to start the engine. And this is done by the pyrotechnic subsystem, and it's a vital part of the avionics system responsible for the control of the flight phases. So Ariane 6 is the very first system that's going to use optopyrotechnics. Okay, so what is that? Optopyrotechnics is when the charge is detonated by a laser pulse. And the advantage of that is that it's going to be immune to electromagnetic interferences, because typically the normal pyrotechnics is it's a voltage pulse or electrical power pulse that's going to detonate the charge, but then it's immune, so it's sensitive to the electromagnetic environment, which means that if you have something coming in there, that actually the thing could explode or could not work on the launching pad. So it's very, very sensitive. So they want to get rid of that. And there's other advantages such as mass and volume and cost reduction. So the thing is, they need to make sure that the path between the lasers and the detonators is clean. So you have optical fibers, and they need to be well connected before you start, when you assemble everything and before you actually launch the device. So you need to be able to check that this is working fine in a way that you're not going to affect these charges there. So you need a device that's going to inspect all of this. And this is done by a technique called optical time domain reflectometry at the single photon level. So in a nutshell, there's a light source which goes into, say, a beam splitter, and light comes back, and there's always some of the photons that are coming back because of a process called Rayleigh backscattering, and then you go in this. So the photons that are coming back are detected by a single photon detector. If you time correlate the time at which you have sent a pulse with respect to the detections, you can know where the photons were reflected in the end. So you map time to space and you see that. So what we have done is a system where it's called as an OTR system, working at a single photon level that has high sensitivity, very high dynamic range, really good spatial resolution, less than 1.5 centimeters, and fast acquisition time. And this is what they needed. We have shown the European Space Agency, when they were looking for a solution, that this was the only solution that could actually work. And this is why they picked that technology. So in order to do that, you need to have these SNSPDs. And the ones we use are polarization sensitive. They have low dark count rate, non-latching behavior. I'm not going to go into the details. And we have a system that's autonomous. And we made a system that produces traces like this. When you see the connectors, these green dots are the connection between the different optical fibers, and you see what's happening in there. And you can map the inside of a fiber just by looking at it remotely after it was assembled. And there's a software that looks at the whole thing, identifies the peaks, and makes sure that everything is at the right place. And it's going to produce a report that you can put in the hands of an operator, where you have a pass and fail status with no human interaction required, and you have a high reliability. So this is a successful test report, and this is a failed test report. There's a peak here that shouldn't be there, which is indicative either of a problem with the fiber when it's pinched, or the wrong cable was put in there, so the device can actually do that. So things are underway. There was a first test done in your part of the world. I mean, it's not that close to Buenos Aires, but it's still on your part of the world, in French Guiana, in Kourou, where this launch pad actually is. So it's the first successful test of firing a booster using the solution that we have developed at IDQ. So it's very cool to see that superconductivity and single photons and this kind of technology can be used for a very demanding application. The physics is one part, but making a device that you can put on launch pad that will have a role to play in the assembly of a launcher and basically help it launch and go through the right sequence is quite cool to see that that technology can make it to something like this. And I think we're going to see a lot more of quantum technologies and applications like this, because the extreme applications emerge more and more, and they're going to require these high-performance devices. Okay, so I'm not going to talk about this. I'm running out of time. Let me just recap. 46 minutes, I see. So I spoke about IDQ's QRNG chip and its security. Spoke about the detailed model of the origin of the quantum entropy. We get near optimal entropy with proven security with robust operation, and it's now in mobile phones and soon in a lot more devices. I also spoke about superconducting nanowire single-photon detectors that offer excellent performance. I didn't have the time to speak about QKD, sorry about that, but I did speak about the space launchers, and I hope this was of interest to you. And with this, on behalf of everyone at IDQ, so a picture taken in the Swiss Alps, very beautiful place. You also have beautiful mountains in your part of the world. Maybe one day I'll get to see them. I want to thank all of our collaborators, and I want to thank all of you for your attention, and I'll be happy to take questions if there's any.
Okay, thank you very much, Felix, for your talk. It was excellent, very, very impressive what you are doing. I think we have a question. We have a couple of questions. I don't know if Miguel is there. He has to leave, so I'm gonna pass it to him first, and then we go to the rest. Hola, hola. I don't know if he's listening. Well,
He did a question in YouTube, I think, right?
Yes, but he connected to ask it himself. Well, we pass to Christian. Christian, do you want to ask your question?
Yeah, thank you very much, Felix. Beautiful and interesting talk. I have two questions. I will do the first one. The first one is on the second part, on the single-photon detectors. You showed that you can build them in such a way that they are sensitive to different wavelengths. And here my question is split-wise. So the first thing is, what do you change so that it makes it more sensitive to one wavelength or the other one? What changes in the physics in the device? And the other question there is, can you reach good sensitivities also in the visible or near UV region, or are you limited to near infrared?
Okay, absolutely. I'll be happy to answer that question. So the first question is how, what changes from this to this? Well, actually, as I was saying, the device itself is, whenever a photon is absorbed, it's going to work. One photon can be sufficient to trigger, one photon at 800 can be sufficient to generate this hotspot that makes a trig. But for the same material, if a 1550 nanometer photon is absorbed, it's also going to work. The trick is to get the photon to be absorbed in a nanowire. So you do have to make I'm not showing it here, but there's a planar cavity. It's not mirrors, it's just stacks. In the clean room, you have a mirror, you have, let's say, a silicon dioxide layer, and then an SNSPD, and maybe a bit more of silicon dioxide or things like this you can play with, which creates what's called an impedance match cavity. So you have a reflection on the first surface, which has a low reflectivity, then sunlight goes inside, and then you have also reflectivity on the layer itself, and then the mirror underneath, which has a very high reflectivity. And if you tailor the stack properly, you can make it such that the reflections outside interfere destructively, even though the first mirror is not a high reflectivity mirror like you would have in a feathery cavity. So this trick can be played. This is called an impedance match cavity. And if you have this, the photon stays inside until it's absorbed in the weakly absorbing layer. So the layer maybe is going to absorb in itself with a property of maybe 10%, maybe a bit more, it depends on the thing. But if you have the photon staying inside the cavity, you can bump the efficiency to 99%. Now this cavity has a spectral response. So when it's optimized for this, it's not optimized for this one, and vice versa. So that's the first thing. And then the second thing is the optical fiber type you actually put is also going to play a role, because optical fibers are single mode over a certain range. But if you go too far on one end or the other, they're not single mode anymore, or they may have too much attenuation. So this is how you tune that. But you cannot have with a cavity something that is flat over the whole region, but you see that's actually flat over a pretty broad region. Now the second question, can you repeat it again, please?
So the other question was if you can also go to the visible or UV, near UV.
Oh, yeah.
Right?
Absolutely, absolutely. So I'm not showing it here, but this device is going to detect down in the UV. Now this device is not optimized, specifically for the UV, but it's possible to get towards very high efficiencies in the UVs as well. And you're probably asking this question because you're using ion traps where UV is definitely an application. So there's a group in the US, NIST, and I think the group of maybe Chris Monroe, I think, if I'm not saying anything wrong, they have made SNSPDs integrated into the traps themselves, made for UV. So you have the detector directly in there to actually detect the UV photons for an ion trap application. So this is definitely one of the applications. There's a lot of applications for SNSPD. This is one of them. And so you have that. You can also go on the other side. So recently, a group in NIST, which are really good, they have demonstrated SNSPD operation at 10 microns light. So this is really far into the infrared. So that opens up a bunch of applications in that sector as well.
Okay. Gustavo, ¿querés aprovechar y leer alguna de las preguntas? No sé si hay alguna otra pregunta acá en el Zoom.
Yes.
Después si no volvemos. Now we go to questions that are in the YouTube channel, Felix.
So I'll go with the second first because I'm not sure if Miguel is going to connect at some point. So Diego Gross asks, why do you need such a high sensitivity for conventional OTDR application? I understand the tighter requirement on spatial resolution given the short distances involved.
Yeah, this is a very good question. Thanks for asking it. So there's a bunch of things that actually make the high sensitivity necessary. One of them is that, well, first of all, this optical detonator is detonated by light. So you want to make sure that when you send the right amount of light into it, it's going to do its job. Now, if you probe the whole thing with light, you want to make sure you don't damage it. So you have to operate at very low light level. So what comes back is photons, not strong signals. And of course, there's a big safety margin here, but it's quite crucial because if something goes wrong, the whole thing can be lost. So so there's that. So you need to have single photon detectors. Now, the type of optical fiber used in the system also make it so that you end up losing a lot of light in the interface in there. Okay, so you also need to compensate that with the high efficiency. And the second thing is you want it to be free running. So this is a detector that doesn't need to be gated. So it's just looking all the time. And by doing that, you can probe the whole thing all at once, or let's say you can probe it much faster. Because if you have a gated detector, then you have to move the gate to look only at one section at a time, and that's actually quite slow. And they want this to be really fast because it's a question of time of integration that needs to be reduced. And if they want to have a good enough rate at which they can use that launcher, then it needs to be quite short. And cost minimization is the thing. So you need to have something that's efficient as well in order to minimize the time necessary to scan not only one but up to close to 100 fiber trains when the whole thing is assembled. So the whole thing, did I show? It says, oh yeah, this here. This, you're going to connect the optical fibers in here, and you're going to test a lot of fibers in parallel, and then end up doing what you need to do in a short amount of time. So that's why the SNSP is actually the only technology that was working for that. So it's free running and high efficiency for the crucial features, even though it's a short distance.
Okay, thank you. And I have a question as well about your single photon nanowire detectors. Would it be useful to use high temperature superconductors, or the temperature noise is already something that you wouldn't like?
Well, that's a very good question. Thanks for asking it. So indeed, so this is working at 0.8 Kelvin. Okay.
Yes.
It's not that cold in a way, like in a sense that it's not that difficult to get to 0.8 Kelvin. We have a system that does it. It's turnkey, right? And the TC is about 5 Kelvin. Okay. Now it turns out that with SNSPDs, and there's no general rule out there, but if you look at the different materials that are being used for SNSPDs, they operate best at around 1/5 the TC. Okay, so around 1 Kelvin. They do work still at 2.5 Kelvin, and we have shown that into a different experiment. But you kind of lose a bit on the time resolution, so they're more comfortable at 1 Kelvin, 1.5 Kelvin in that range. And they're really comfortable as 0.1 Kelvin. And other materials are similar. So for TC of, let's say, 50 Kelvin, something you can get, with MGB2, for instance, when you package it and so on, it's been demonstrated that you can have single photon response for visible at around, few kelvins, maybe up to 5 Kelvin, not too more. So the physics in itself does not necessarily allow you to be operating just right under the TC itself. It doesn't work so much.
Okay.
Now, this is fascinating topic. There's some people trying to still, do it with evacuo. So high MGB2 has been demonstrated. Evacuo is really challenging. These materials, they oxidize very, very quickly, and they're very sensitive. So very fascinating topic. It's difficult. Maybe there's going to be something in the future, but right now it's not done yet. It's more challenging than doing it the way we do it.
Okay, thanks. Also, if you need to be like at 1/5 of the TC, then you won't ever use liquid nitrogen, for example. I mean,
no. And I don't want to claim that this is a general rule. Okay, so don't quote me on this. The only thing I can say is if you look at what's out there, that's what we see. At least for the low TC materials. So whether this applies with high TC materials, maybe. I would imagine that the physics is not that different, although the physics is not perfectly understood, like high temperature superconductivity things. But if the same thing applies, then you'd have this constraint as well. This being said, if something was working with exceptional performance at 10 Kelvin, 10 Kelvin really allows to decrease the cryogenics, size and cost, and so on. So this would be a game changer, even 10 Kelvin.
okay.
So hopefully this can be achieved in the near future.
¿Nos quedó entonces una pregunta del YouTube o no?
Only the one from Miguel. Maybe I can read
Sí,
it.
entonces hacela porque se debe haber desconectado.
So there is also another question in YouTube. What is the typical, this is for the first part of the talk, I think. What is the typical readout noise of the mobile phone camera you showed at the beginning? Is the detection statistics Poissonian even for low intensities? This is close to darkness.
Yes. So, well, this is that slide here. So this is the ADC code. So it's the output of the 10-bit ADC. If you have light, then you're going to be seeing this distribution here, which is dominated by the Poisson nature of the light. And if you switch it off, you're going to still have a little distribution that's close to 0, but it's not equal to 0. And this is the dark noise. This is these electrons that come in here that are, and then the output signal is mixed with the voltage noise. So you see like the center is close to 10 with respect to that. So it's much narrower than that. So what you see here is the contribution of the photons plus that noise, but this contributes to very little in there. And actually, even if you assume that this contribution is given by the attacker, I was showing that the entropy is not, is still the same. It's really, the entropy is purely quantum or almost purely quantum. At least very close to being optimal, and that's sufficient for a quantum entropy source or an entropy source to put that into a security application after that.
Can I add a question to that? So, but the chip that you're doing has the CCD and the LED integrated, right?
Oh, yeah. Yeah, so I didn't mention it explicitly, but thanks for asking us this question. Indeed, the chip has, that's the chip. It has the LED, the CMOS image sensor, you know, what comes afterwards as well. It's all in there into this little package.
Okay, and can you comment a bit on the package and the optics of it and how it's?
So it's definitely opaque, so no light is coming through. Okay, here's a small image. That's 2.5 by 2.5 approximately. So it's opaque, no light is coming through. It's a, you know, that's about the size it has if you look at it compared to the cell phone. That's just a composite image, right? The chip is not there. The chip is inside. It's just put in here so that you see approximately the size with respect to the phone, but it's inside, soldered on the PCB, and it's opaque. Only the light coming from the source inside is being detected.
Okay, but is it like a single chip thing, or is it the multiple? Do you have like really arrangement of optics in there? Or is it all done on?
So essentially, you have there's no optics. The LED is illuminated, you know, with enough uniformity so that the sensor can be exposed with sufficient uniformity so that all the pixels are falling in terms of intensity within that range, right? So for all the pixels, even though they're not illuminated with the same intensity, they all have the same entropy coming out of each of them.
Okay, thanks.
So no lenses. It's you know, to make it small, you really have to work on the package, and you can have the LED, you can have the sensor, all of this, and have this one exposition.
Now that we're at it, let me do a final question with respect to this. So you were telling us at the beginning that you were telling us how one works at such a company as ID Quantique, and I was wondering, so for example, with this kind of things, the foundry, so this kind of things you commission over out to other companies, right, to get them done. So that's, I guess, the design.
Yeah, we don't have the foundry.
ID Quantique, and
that's right. So well, I mean, so ID Quantique, IDQ's role in this is essentially, you know, recognizing the technology, going ahead and you know, do some patent protection if that's useful, which is the case here. So it's a patent, it's patented, and then you go and you do the design, and then you definitely have to work with external partners in order to realize the different parts and integrate and testing and so on. So it is not something that IDQ is making in its own clean room. As you can imagine, it's outsourced. But that's typically how the whole industry works for these things. And there are some controls, of course. You know, when it's a security device, you want to make sure that the whole supply chain is going through some rigorous checks and so on, and this is the case here.
thank you again.
Okay, I don't know if we have more questions.
Not from YouTube. And
Okay, I don't know if there is more questions here. If not,
maybe a small last question. I want to. I think it comes in the same line that Christian asked a second ago. Concerning the nanowires and all the kind of detectors, the scale, the image you show, that's a wafer, or that's just a picture? Can you? I don't know how much you can comment on that, and use EBL or?
Yeah, that's a good question. So what you see here is only the active portion of the SNSPD, this parallel SNSPD. You see the size of this is about, I think it's 16 micron by 16 micron. This is where the optical fiber is put on top, goes in here, and this is an SEM image of that. So this is patterned with e-beam lithography, indeed. The device itself, I don't have any pictures to show, and apologies for that, but the device itself, this is contacted, you have the electrodes coming out. In the case of that device, this parallel device, in order to make it work, you have to play tricks around, which I'm not showing. They're quite beautiful images, but I don't have anyone to show. But these devices, as I was saying, the width of the nanowire is around 100 nanometers, and the thickness is about maybe 5 to 10 nanometers, something like that. So e-beam lithography to pattern it, and then etching. The rest can be done with thin film deposition, lithography, and of course, basically to get to very high efficiencies and properly claim that you have all of this, there's all the optics that you need to develop and maintain. This is in the end a metrological measurement that we're implementing, a difficult one. It looks easy to measure the efficiency of an SNSPD, but of a detector, it's actually very easy to mess it up. When you say it this way, be wrong in one direction or the other. So we really pay a lot of attention there. But in terms of the technology, it's a clean room, thin film, lithography, e-beam lithography, and material physics.
Thank you, Felix.
Okay, I think we are pretty much done with the questions. So thank you, Felix, for your excellent talk, the very nice seminar. So we appreciate it. Thank you very much. Now I ask you to stop sharing because Gustavo will be presenting the next seminar we have next week.
Yes.
Thank you, Felix.
Thank you so much. I really appreciate the opportunity to be able to give this presentation, and I hope you like it.
Thank you.
Thank you. So, la próxima charla para la semana que viene va a ser un coloquio de Lisa Chisari. Ella es argentina y ahora está en Holanda, en el Institute for Theoretical Physics of Utrecht University, y nos va a contar sobre el universo a través de las formas de las galaxias.
Bueno, nada, gracias a todos por estar y nos vemos el jueves que viene. Thank you, Felix, for being here.
My pleasure.
Bye-bye.